In just about 25 years, Japan could nearly run out of space to bury its waste. A country widely known as one of the cleanest in the world is now facing enormous pressure from the very waste it generates. To survive, Japan has been forced to turn waste into resources. Here, garbage is sorted under extremely strict rules and separated into individual material streams. From there, each stream is sent to recycling plants, organic waste treatment facilities, or modern incinerators capable of converting waste into electricity. How can a country maintain such tight control over tens of millions of tons of waste every year, while its remaining landfill capacity continues to count down? Join Factron Process as we step inside the waste sorting and treatment system operating across Japan. Do you think Japan recycles its waste using extraordinary technology? In reality, the ultimate foundation of this system is not found inside a factory. It begins with the sorting discipline of the community. In many residential areas, even a single incorrectly sorted bag of garbage may be marked with a warning label and left behind at the collection point, forcing its owner to take it home and sort it again. This strict enforcement has created one of the most tightly controlled waste management systems in the world. To keep this enormous machine operating, Japan must process approximately 38.11 million tons of municipal waste every year, equivalent to more than 100,000 tons per day. Across the country, hundreds of recycling facilities and nearly 1,000 waste incineration plants continuously turn old paper into cardboard, PET bottles into recycled plastic, and metal scrap into new raw materials. Meanwhile, waste that cannot be recycled is converted into heat and electricity. But before waste can become either raw material or energy, the entire journey must begin with the stage that determines the quality of the whole system: sorting at the source. In Japan, the recycling journey does not begin with robots or conveyor belts. It begins inside the kitchen. Before a collection truck even arrives, residents must separate their waste into numerous categories, including burnable waste, non-burnable waste, paper, cardboard, PET bottles, glass, metal cans, plastic packaging, batteries, light bulbs, and bulky waste. Each municipality follows its own sorting rules and collection schedule. One of the strictest examples is the town of Kamikatsu, where waste is separated into as many as 45 different categories. Here, a water bottle is not treated as a single object, but as 3 separate material streams: the PET bottle body, the cap, and the label. Before being taken to the collection point, the bottle must be emptied, lightly rinsed, uncapped, and stripped of its label. Why go to so much trouble? Because in recycling, cleanliness can sometimes be more important than volume. Just a few incorrectly discarded items can reduce the quality of an entire batch of material, jam equipment, or even cause fires and explosions. For this reason, Japan's first and largest sorting facility is actually the millions of kitchens where residents clean, dismantle, and separate their waste into individual material streams. But sorting correctly is still not enough. Waste must also be placed outside on the correct day, at the correct time, and at the designated collection point. In many residential areas, waste suitable for thermal treatment is generally collected around twice a week. Non-burnable waste, PET bottles, paper, cans, and other recyclable materials follow separate schedules, commonly ranging from once a week to once or twice a month. Residents are usually required to bring their waste to the collection point before 8 o'clock in the morning, sometimes using a specific type of bag required by the municipality. A bag placed outside on the wrong day or sorted incorrectly may be marked with a warning label and left behind. Bulky items such as tables, chairs, mattresses, and cabinets must be registered in advance, paid for, and marked with a special disposal sticker. After completing its route, the collection truck carries each type of waste to the appropriate receiving facility. There, the material passes through a second layer of control. Workers and mechanical separation equipment remove incorrectly discarded items, dirty packaging, batteries, sharp pieces of metal, and other contaminants that could damage the machinery. valuable paper, plastic, metal, and bottles are separated into individual streams before being shredded, compressed into bales, or transported to specialized recycling plants. Material that fails to meet the required standards is downgraded, sent for thermal treatment, or transferred to a final disposal route. From this point onward, the waste streams no longer travel together, but begin completely different treatment journeys. Paper and cardboard are among the most heavily recycled material streams in Japan. Cardboard alone can achieve a recovery rate of nearly 98%, meaning that most used cardboard boxes have a chance to return to the recovery system. After being collected separately, newspapers, magazines, office paper, and cardboard are sorted according to quality. They are then compressed into bales weighing hundreds of kilograms to reduce the volume required for transportation. At the mill, the bales are dropped into enormous hydraulic pulpers, where water and rotating agitators break the paper apart into a thick fiber slurry. Screening systems then remove staples, adhesive tape, plastic, and metal. For certain types of printed paper, the pulp also passes through a de-inking stage. Chemicals and air bubbles are used to lift ink particles to the surface, where they can be skimmed away. After cleaning, the pulp is spread into a thin layer, pressed to remove water, dried across a series of heated rollers, and wound into new rolls of paper. Old cardboard is commonly transformed into corrugated medium, paper cores, or new shipping boxes. At some Japanese manufacturers, cardboard-based paper may contain as much as 98% recycled fiber. This figure refers to the fiber content of certain types of base paper, not the average recycled content of Japan's entire paper industry. However, this cycle cannot continue forever. Each time paper is repulped, its cellulose fibers become shorter and weaker. As a result, the paper cycle still requires a certain amount of virgin fiber to replace fibers that have deteriorated or been lost. The delivery box arriving at your door today may contain fibers that have already passed through several generations of cardboard boxes. But if old paper can be reduced to pulp and begin another life, what happens to the billions of transparent PET bottles discarded after use? From a country where less than 1% of PET bottles were collected in 1993, Japan achieved a remarkable transformation. By fiscal year 2020, the collection rate had reached 96.7%, while the recycling rate had reached 88.5%. The secret lies not only in public awareness, but also in product design. In Japan, PET bottles are essentially born to be recycled. Their bodies are completely transparent. They are not mixed with other plastic contaminants. Their labels are extremely easy to remove, and ink is not printed directly onto the bottle itself. This intelligent design creates an exceptionally clean input stream for the two main recycling technologies: mechanical recycling and chemical recycling, in which the plastic is broken down into its original building blocks and then synthesized again. However, Japan still faces a major challenge. At present, only around 15% of old bottles are recycled through a closed-loop process into new food-grade bottles. Even so, major companies such as Suntory are racing toward an ambitious target, using 100% recycled or plant-based plastic by 2030. Japan is not only highly advanced in plastic recycling, it is also a master at bringing metal waste back to life. Despite having limited natural resources, the country maintains some of the world's highest metal recycling rates. The process is extremely strict. Metal scrap is shredded and automatically separated using magnets or eddy current systems. The separated materials are then sent into furnaces operating at temperatures of thousands of degrees Celsius, where impurities are vaporized before the molten metal is cast into new bars of purified material. Japan's creativity was clearly demonstrated during the Tokyo 2020 Olympic and Paralympic Games. Approximately 5,000 medals were made entirely from metals recovered from electronic waste. More than 6 million mobile phones and other discarded electronic devices were donated by people across Japan so that every gram of valuable gold, silver, and copper could be extracted. From this, the concept of the urban mine emerged, a place where precious metals are not buried underground, but hidden inside products that have reached the end of their useful lives. However, not every type of waste can be melted down. When it comes to food waste, treatment facilities must rely on an entirely different force: microorganisms. One way Japan reuses organic waste is by converting it into compost. However, if food waste is mixed with plastic, metal, or chemicals, reuse becomes almost impossible. For food waste streams that have been collected separately and meet the necessary standards, the first step is to remove bags, containers, and foreign objects. The remaining food waste is then shredded to create a more uniform particle size. During aerobic composting, microorganisms use oxygen to break down carbohydrates, proteins, and fats. The material naturally heats up as decomposition progresses, provided that the temperature is maintained for long enough and the entire mass is turned evenly. Workers must carefully control moisture, temperature, oxygen levels, and the carbon-to-nitrogen ratio. If the mixture becomes too dry, microbial activity slows down. If it becomes too wet, oxygen levels fall and unpleasant odors begin to form. However, compost is only one of several possible outputs for food waste. Japan's food recycling law also promotes converting food byproducts into animal feed, fertilizer, and energy. Under official guidance, food waste delivered to animal feed or fertilizer production facilities is counted as recycled material. But there is still a troubling contradiction. Japan continues to discard millions of tons of food that could still be eaten every year. For that reason, the most effective form of food waste management may not always take place inside a treatment plant. It may simply be preventing food from becoming waste in the first place. For dirty mixed waste that cannot be recycled economically, Japan turns to a far more powerful solution: fire. Many people may assume that nearly all waste in Japan is recycled. However, in fiscal year 2024, the municipal waste recycling rate was only around 19.3%, equivalent to approximately 7.38 million tons. So where does the rest go? Materials that are too dirty, complex, or no longer valuable enough to recycle are sent to thermal treatment facilities. The waste is emptied into a storage pit where grab cranes continuously lift and mix it to balance moisture and heating value before feeding it into the furnace. The waste burns on a moving grate under a carefully controlled supply of air. Incinerators commonly operate at around 850 to 1000 degrees Celsius, destroying most organic material and pathogens, while reducing waste volume by approximately 80 to 90%. Heat from the furnace is recovered through a boiler to produce high-pressure steam, which spins a turbine and generates electricity. The electricity first powers the facility, while surplus power can be supplied to the grid. Excess heat may also serve swimming pools and other public buildings. As of March 2025, Japan had approximately 991 waste incineration plants. Of these, 415 recovered energy with a combined generating capacity of approximately 2.289 gigawatts. However, this is energy recovery, not material recycling, because paper and plastic cannot return to their original material cycles once burned. The exhaust gases may contain dust, acidic gases, nitrogen oxides, heavy metals, and other hazardous compounds. Lime is injected to neutralize hydrogen chloride and sulfur oxides, while activated carbon absorbs mercury, dioxins, and certain organic compounds. Fine dust and ash particles are then captured in fabric bag filters. Some plants also use chemical reagents and catalysts to reduce nitrogen oxides. Sensors continuously monitor emission levels before the treated gas is released through the stack. Fly ash usually contains more pollutants than bottom ash, so it must be stabilized or solidified. Bottom ash is cooled, screened, and passed through magnets and eddy current separators to recover iron and aluminum. The remaining ash and residues are transported to final disposal sites. Although incineration reduces waste volume by approximately 80 to 90%, this material still consumes Japan's landfill capacity, currently estimated to be equivalent to only about 25 years of use. That is how Japan has transformed a country running dangerously short of landfill space into one of the world's leading examples of a circular economy. But the story of recycling does not end there. Among the millions of tons of waste recovered every year lies a special stream containing materials far more valuable than most people realize: electronic waste. Old phones, computers, and circuit boards may appear to be nothing more than scrap, but hidden inside them are tiny quantities of real gold. So how do factories extract those microscopic amounts of gold from tons of complex electronic components? Join us on the next journey as we explore how e-waste is recycled and transformed into gold. Waste capable of poisoning soil and water for decades can, when processed correctly, be transformed into gold bars worth millions of dollars. It is a journey in which what the world throws away becomes one of the most valuable resources in modern industry. To release the gold locked inside obsolete devices, every phone, computer, and circuit board must be torn apart, crushed, and separated into distinct material streams. In the end, what was once buried within electronic waste is reborn as gold bars of near-perfect purity. Join Factron Process as we step inside the production line where electronic waste is ripped apart and reborn as a valuable resource. Every year, humanity is not simply discarding old electronic devices. We are throwing away an enormous reserve of valuable metals. In 2022 alone, the world generated about 68 million tons of electronic waste, enough 1.5 million trucks, each carrying 44 tons. Lined up bumper to bumper, that convoy could stretch around the Earth's equator. Yet only 22.3% of this waste was officially collected and recycled. Hidden beneath plastic casings, electrical wiring, and burned-out components are copper, silver, palladium, and above all, gold. Even more surprising, 1 ton of electronic circuit boards can contain 40 to 800 times more gold than 1 ton of natural gold ore. That is why electronic waste is increasingly seen as a form of urban ore, a vast resource already sitting inside the devices we use every day. At ERI's electronics recycling centers across the United States, more than 550 tons of electronic waste can arrive in a single day. To process that enormous volume without confusion, every device must pass through the same starting point, the receiving area. This is where the recycling journey officially begins. As soon as a truck reaches the facility, forklifts unload each pallet into the receiving zone. Every shipment is weighed, its origin is recorded, and a unique identification code is assigned so it can be tracked throughout the entire process. In modern recycling plants, this system does more than control the number of devices. It creates a complete record of each load's journey, from the moment it enters the facility until recycling is complete. Technicians then carry out a rapid inspection of each device. Some computers, monitors, and servers may still be functional, so they are set aside for repair or reuse, extending their service life by several more years. Only equipment that can no longer be restored moves forward into the recycling line. Before any device can advance to the next stage, one final requirement must be completed: data destruction. Hard drives and solid-state drives are either wiped according to international data security standards or physically destroyed when they contain sensitive information. Only after every trace of data has been securely removed is the old computer truly ready for the next stage. After being inspected and logged in the receiving area, the electronic waste is transferred to the dismantling line. At the dismantling station, workers use electric screwdrivers with torque control to remove every screw from the device. In just a few seconds, dozens of screws can be removed without cracking the circuit board or damaging the components inside. Once the outer casing is opened, the lithium battery is always removed first to eliminate the risk of fire. Next come the hard drive, power supply, memory modules, processor, and motherboard. As soon as each component is removed, it is placed into its own designated sorting bin, allowing the entire operation to flow continuously while minimizing material mix-ups. This sorting process does more than improve recycling efficiency. It determines how every material will be processed in the next stages. Steel, aluminum, and plastics are routed to separate recycling lines, while printed circuit boards, processors, and memory modules, components that contain far higher concentrations of copper, silver, palladium, and especially gold than the rest of the device, are set aside for precious metal recovery. In many modern facilities, the initial dismantling of a desktop computer takes only about 3 to 5 minutes. Dedicated processing lines can handle tens of thousands of devices every day before they move on to the next stage. After dismantling, all remaining components are fed into an industrial shredding system to reduce their size and free individual materials from the original structure. The process begins with a dual-shaft shredder. A conveyor continuously feeds the material into the shredding chamber, where 2 steel shafts fitted with dozens of alloy cutting blades rotate in opposite directions with extremely high torque. Rather than slicing at high speed, the blades slowly grab, tear, and crush steel housings, aluminum frames, cables, remaining circuit boards, and plastic parts into smaller pieces. This low-speed, high-torque design is capable of processing even the toughest materials while significantly reducing dust generation and the risk of sparks. After the first stage of shredding, the material is reduced to pieces about 3 inches in size before entering a hammer mill. Inside, high-speed steel hammers repeatedly strike the material until the entire mixture is small enough to pass through a 0.8-inch screen. This nearly uniform particle size is critical for maximizing the efficiency of the magnetic separators, eddy current separators, and optical sorting systems used in the next stage. By the time the material leaves the shredding system, thousands of electronic devices of every shape and size have been transformed into a single, uniform stream of recyclable material, ready for further processing. After shredding, the mixed material passes through a series of automated separators. First, an overband magnet pulls steel fragments from distances of up to 20 inches and transfers them onto a separate conveyor. The remaining stream then enters an eddy current separator. A magnetic rotor spinning at about 3,000 revolutions per minute throws non-ferrous metals such as aluminum to one side, while plastics and fiberglass fall onto another belt. The recovered steel is sent to steel mills for remelting, while plastics are shredded, cleaned, and converted into recycled pellets. The most valuable stream contains printed circuit board fragments. Although they represent less than 10% of the total weight, they hold most of the gold, silver, palladium, and other precious metals found in electronic waste. The material stream rich in printed circuit board fragments is blended with silica, limestone, and fluxes before being continuously fed into a smelting furnace operating at temperatures above 2,200 degrees Fahrenheit. Within a short time, the intense heat consumes the plastics, epoxy resins, and other organic materials, completely releasing the metals that were once locked inside millions of electronic components. At the same time, glass, ceramics, and fiberglass combine with the fluxes to form a layer of slag that rises to the surface and is skimmed away. The most important role, however, belongs to the molten copper. Rather than becoming the final product, it acts as a metallic collector, drawing in gold, silver, and palladium from countless circuit board fragments and concentrating them into a single molten mass. By the end of this stage, the precious metals that were once scattered throughout the electronic waste have been concentrated into blister copper, preparing them for the extraction process that follows. At this stage, the gold, silver, and palladium are still dissolved within the molten copper. They cannot be separated immediately after leaving the smelter. Instead, the molten metal is poured into large molds and cast into massive anode plates for the next stage of the process. Each plate can weigh up to 900 pounds before being transported by overhead cranes to enormous electrolytic tanks. Inside these tanks is a solution of copper sulfate and sulfuric acid. The anode plates are suspended between sheets of pure copper that serve as cathodes. When direct current is applied, copper atoms gradually leave the anodes, dissolve into the electrolyte, and slowly deposit onto the cathodes. After days of continuous electrorefining, the newly formed copper cathodes reach a purity of up to 99.99%, ready to be used again in electrical wiring, motors, and countless other industrial products. Gold, silver, and palladium, however, behave very differently. They remain almost completely insoluble throughout the process. Instead of entering the solution, they slowly detach from the anodes and settle at the bottom of the tanks as anode slime. This dark residue may look insignificant, but it contains nearly all of the precious metals recovered from thousands of tons of electronic waste. Once electrorefining is complete, most of the gold remains concentrated in the anode slime collected at the bottom of the tank. Although this dark residue may appear insignificant, it contains some of the most valuable material recovered from the entire recycling process. Nitric acid is commonly used first to dissolve silver, copper traces, and several other base metals. Gold, however, requires a much stronger solution. It is dissolved using aqua regia, a highly reactive mixture of hydrochloric acid and nitric acid, and one of the few chemical solutions capable of breaking gold into solution. The gold-bearing liquid then passes through repeated stages of dissolution, filtration, purification, and chemical precipitation. During the final reaction, the dissolved gold separates from the solution and returns as an extremely fine powder with a very high level of purity. This powder is later washed, dried, and prepared for melting. But this stage also requires the strictest environmental controls. Wastewater containing strong acids and heavy metals can remain hazardous for decades if it is released without proper treatment. For this reason, many modern refineries operate closed-loop systems that can recover and reuse between 80 and 90% of their processing solutions, reducing pollution while significantly lowering chemical consumption and production costs. After every stage of crushing, separation, smelting, and refining, this is the moment when the gold finally reveals itself. From tons of electronic waste, the recovered gold has now been reduced to a small quantity of highly purified powder. This powder is loaded into an induction furnace where the temperature rises to approximately 1950 degrees Fahrenheit, just above gold's natural melting point of 1948 degrees Fahrenheit. Under the force of the electromagnetic field and intense heat, millions of microscopic gold particles gradually fuse into a glowing stream of orange gold metal. Throughout the melting process, the furnace temperature is continuously monitored to limit oxidation and prevent the loss of precious metal. A small amount of flux is added to bind with the final impurities, drawing them to the surface as slag, where they can be carefully skimmed away. Only when the molten gold reaches the required purity are the pouring controls opened, allowing the liquid metal to flow slowly into heat-resistant molds that have been preheated to reduce thermal shock and prevent surface cracking. Within minutes, the intense orange glow begins to fade, revealing solid, heavy, polished gold bars. It is difficult to believe that this journey began inside discarded phones, computers, and circuit boards. After passing through dozens of processing stages, they have been transformed into gold bars worth tens of thousands of dollars, ready to return to the market as a newly recovered resource. The newly cast gold bars are not yet ready for the market. One by one, they travel along an automated conveyor into the inspection area, where every bar must pass a series of strict quality checks before it can leave the refinery. First, a high-precision electronic weighing system verifies the exact mass of each bar, ensuring it meets production specifications. The bar then passes beneath an X-ray fluorescence spectrometer, which analyzes the metal composition in just a few seconds without cutting, drilling, or damaging the surface. The system accurately measures the proportions of gold, silver, copper, and any remaining trace elements. High-grade refined gold can reach a purity of 99.99%. Even the smallest deviation beyond the permitted tolerance is enough to reject the bar. It is immediately removed from the production line and returned to the furnace, where it is remelted, its composition corrected, and the refining process repeated until it meets the required standard. Bars that pass every inspection continue to the industrial laser marking station. A unique serial number, exact weight, purity level, refinery logo, and identification code are permanently engraved into the surface, creating a complete traceability record for every bar. They are then sealed inside tamper-evident packaging or protective cases, stacked onto pallets, and transferred to secure vaults before being shipped to banks, electronics manufacturers, and precious metal fabricators around the world. A journey that began with discarded phones, computers, and circuit boards now ends with an internationally certified gold bar, ready to begin an entirely new life cycle with a value thousands of times greater than the electronic waste from which it was recovered. Few people realize that discarded phones, computers, and circuit boards still contain gold, silver, copper, and other valuable metals that took millions of years to form deep beneath the Earth's surface. When these devices reach the end of their useful lives, their value does not simply disappear. Through modern recycling technology, precious materials can be separated from plastics, glass, and common metals, then refined and returned to industries such as electronics, energy, aerospace, medicine, and other advanced technologies. That is why proper recycling is about far more than reducing landfill waste or preventing pollution. It is also a way to preserve resources that nature cannot replace within a human lifetime. A certified recycling process may require complex machinery, high operating costs, and strict environmental controls. But the cost of handling electronic waste incorrectly is far greater, from heavy metals leaking into soil and water to the permanent loss of materials that could have been recovered and reused. And that is what makes the world of manufacturing so fascinating. Behind every familiar product lies an enormous network of machinery, precision engineering, and industrial processes that very few people ever get the chance to witness firsthand. If you enjoy discovering the hidden stories behind the industries that keep the world running every day, subscribe to Factron Process. Many more extraordinary journeys are still waiting for us in the videos ahead.